All right, section 2, properties of exponential functions. So starting off, we're going to talk about the exponential graph transformations, how it could shift up, down, left, right, and we're going to describe some transformations, and then we're going to move into interest. And I think that the transformations will be relatively easy, so we won't spend a whole lot of time on that. But on interest, we are going to spend a bit more time on it, talking about a real world example with a savings account. And then we are going to move into continuously compounding interest. And your homework will deal with some continuously compounding interest problems. So let's talk about this. Starting off, transformations. Now, before we talked about the general form y equals a b to the x, and that is the general form or the standard form that we will use. But sometimes we shift the graph left, right, up, or down. And the rules are very similar to the ones that we used with parabolas. We have an x minus h here, which actually let me talk about them in order. We'll talk about the a first. We'll talk about this one here. When a is less than 0, it's reflected down, right? Think about whenever we would have something like y equals negative x squared, right? That was reflected down, right? Same kind of thing happens there. Next up, we have y equals ab to the x minus h. That shifts it left or right. That's what I was wanting to talk about first. This x minus h, it always does the opposite of what you think it should, right? If it's a negative 5, it means it shifted right 5, right? If it's a positive 5 or a positive like 4, if we had something like y equals 2 times 3 to the x plus 3, that would be a shift left by 3 steps, right? Lastly, we have a plain old k at the end that just shifts us up or down. So if you need to copy those down, pause the video, and I'm going to move on. Number 1, we're going to describe the transformations that occur here. So starting off, let's look at that negative at the front. This negative tells us that it's going to be reflected. Or we could say it's going to be upside down. Either way is good with me. Let's next talk about this positive 2 here in the exponent. Well, that positive 2, it's with the x, and it's always the opposite of what you think it should be. So this is going to be left 2. And lastly, we will have this positive 3 here, which means that we're going to go up 3. Now that positive 3 there also changes the asymptote. That's what I had written up here in light blue. Normally the asymptote is at the x-axis at y equals 0. For this one, the asymptote would be at y equals 3 because it shifted that whole graph up 3. So instead of at y equals 0, it became to be y equals 3. Now, we could graph these by hand, and that would be a good thing to do. Maybe it would help us with some of our algebra skills, but from now on, I'm happy if you just type them in a calculator and a graphing calculator and get those. You can use an app on your phone if you'd like to, or you can use your TI calculator. If you need any help typing those in, let me know and I'll help you out with that. So those are the rules for transformations on exponential graphs. And now we're going to move on into interest. Now, I don't know how much you have already learned.
Mr. White, call the office, please. Mr. White, call 1600.
I don't know how much interest you've learned about before, so I'm just going to review this. But this part here that I'm going to do won't actually be on homework. But I do think it's good to think about and to know. So for interest, and I like to think about interest with money. I think that makes a lot of sense for me. The general form or the general function that we're going to use here is A equals P. Well, I'll just let you read that. Right? And this N and T there is in the exponent. So what does this mean? Well, A is the amount in the account now, like right now. And I put the now in quotes because sometimes whenever we have word problems, now is a relative term. You kind of think about, well, what is now? Is now 5 years from now, or things like that. Um, P is the principal amount, the initial amount, right? That's what we started off with. In one of the previous videos, I talked about I think it was like problem 13 from the homework. It was about birds that were going extinct or something like that. And the principal there, the starting, was 200,000. So while I like to think about this with money, you could think about it with other things. So P is the starting amount. R is the rate, like how fast is it increasing, how fast is it decreasing. T is time. Normally you measure the time for this in years if we're talking about money. And then N, and this is where it gets kind of confusing, I think. N is the number of times interest is applied within the time period. So if you have a savings account, you probably about once a month see that a little bit of money is deposited in the savings account. You probably don't have a whole lot, maybe it's a few cents, maybe it's a couple dollars. But every time that you get that money deposited, they have ran the calculations, they've ran this calculation, and they've figured out how much interest to give you. So that's how we do N. For money, for savings accounts, it's almost always every month. Okay. So I want to do just a little example, and like I said, this isn't necessarily on the homework, but I think it's good to know. I always see pictures and little memes and things about talking about how in school you're never taught about money, so I just wanted to show you this here. So say we have a savings account, and we're going to put $100 in it, and the savings account gives us 3% interest, which is pretty good. Normally you won't get a full 3%. It's compounded monthly, which is very normal. Pretty well, if they don't list it, it's going to be monthly. And you keep the money in there 3 years. Now, these functions and these problems get really difficult if you say things like you're going to add money to it every month or something like that. For this one, we're just going to say you put the $100 in it, and then you set it and you forget it. You don't do anything about that account. You let the account do its thing. So we're going to see how much money do you have after 3 years in that savings account. So the principal amount is the starting off amount. That's going to be 100. The rate of interest, that's going to be 3%, but we want that as a decimal, so that's going to be 0.03. Time is going to be 3, because that's 3 years. N is going to be 12, because there are 12 months in a year. Right? N is the number of times interest is applied within the time period, and a lot of the time that will be 12. So let's plug this into that formula up there. We're going to have A, that's how much we're going to have after our 3 years. That's why I'm saying the now is relative. It's kind of, I like to think of it as now, but now really is in 3 years. So A equals 100 times 1 plus the rate, 0.03 over 12 to the 12 times 3. Now from here I can say, well, A is, I'm going to simplify what's inside my parentheses, 100 times, I'm going to get my calculator out, I'm going to say 1 plus 0.03 divided by 12, and I get 1.0025 to the 12, well, 12 times 3 gives me 36. Now, you might also look at this and say, well, this does not represent 3%. What does that represent? That represents, well, we have 0.0025. That's 0.25%. Right? Why don't the banks just say that you get 0.25% interest? Which one sounds a lot better, 0.25% or 3%? Right? You kind of have to understand, what does that 3% interest mean? That 3% means it's 3% divided by the 12 months, right? So they could say that they give you 3% after the year, right? That would make sense, but it actually, every time it's compounded, it's much less, right? So that's something to know. That's something that I know that I did not understand. So right here, I'm just going to type the rest of this in. So I'm going to type in 100 times 1.0025 exponent 36. And I get A equals 109.4051. So that would be $109.41. All right. So over those 3 years, it was earned $9.41 about. Right. So that's a good thing to know. That's a good thing to recognize. I talked about the percents and stuff. If you're wanting to do math on your savings account, you should look, and somewhere online they'll be able to tell you that. They'll be able to tell you how often it's compounded and things like that. So yeah, hopefully that helps out. Hopefully that sheds a little bit of light on how savings accounts work. Moving on. This here is the stuff that your homework will be over. Continuously compounding interest. Now, up here, it was interest that was compounded at specific times. For our example, it was every month, right? Here it's compounded continuously. It is always increasing, or it's always being the math for it is always being done, right? It grows much faster than the monthly compounded one. So our formula here is A equals PE to the RT. Now this E here is a new letter, or a new number there. That's a constant. It's kind of like pi, where pi just kind of crops up in different places, and pi is this really long, irrational constant that we use in different places. That's the same thing with E. And if this is your first time seeing E, just you can expect to see it for the rest of your math career. It's just one of those numbers that pops up in different places. A is the amount in the account, quote unquote now, just like before. P is the principal, or the initial amount. R is the rate of interest, and T is the time, normally measured in years, right? So number two. And number two is it's set up a lot like how some of the homework problems are set up. Find the amount in a continuously compounded account for the given conditions. The principal, the initial investment, is $5,000. The annual interest is 6.9%, and the time is 30 years. So we're just going to plug this all in. We're going to be finding the amount, quote unquote, now. The principal is $5,000. Then we have E, because it's compounded continuously. R is, what is that, 6.9, which would be 0.0069, right? Yes. E to the 0.0069 times our time, which is 30 years. Now I'm just going to type this whole thing in my calculator, and I will get 5,000 times E. And normally on a calculator, it has a E button on there. Actually, I think almost all calculators have that on it. On mine, it is on I have a TI grapher that I'm using. It's on the right side. It's with the division sign. If you have one of the TI-30X2, which is kind of the smaller one that I normally suggest to people, it is right above the pi button on the left. So typing this in, I do 5,000 times E to the 0.0069 times 30, and I get 6149.91. So there we are, $6,149. Right? Again, that's like some of your homework problems, specifically like numbers 5 and 6. So moving on. Number 3, HG197 is used in kidney scans. It has a half-life of 64.128 hours. Write the exponential decay function for a 12 milligram sample, and then find the amount remaining after 72 hours. So these are half-life problems. You might see them in some of your science classes as well. This is the general formula that we will use here. Right? where where h is the half-life listed here in hours. A is the initial amount, right? Just like we've always had, it's the initial. B is 1/2 because we're talking about half-life. So how fast does the half-life happen, right? So it kind of makes sense that B would be 1/2. And the X is going to be the number of hours that we actually like run the experiment for, run how long we set it, right? Um, so the half-life that they give us here, that's specific to Hg197. Is that hydrogen? I think that's hydrogen. Maybe not. And then this X equals numbers of hours. That's how many hours occurs, right? So find the amount after 72 hours have occurred. So they took this element or whatnot, and they have 12 milligram sample of it. They set it on the counter for 72 hours, and then they go back and they weigh it. And we're going to predict what is going, how much is going to be there. I guess it's not necessarily weighing, but you know what I mean. So y is going to be what we're going to be getting from it. So y equals A, our initial, which is going to be 12 milligrams, times 1/2 to the x. X is the number of hours, it's 72 hours, over 64.128. Right? Now, I'm going to type in my calculator. Starting off, I'm going to do 72 divided by 64.128 to make that a little bit prettier. So this is going to be 12 times 1/2 to the 1.123. Now I'll type in my calculator 12 times, and I'm just going to do 0.5 to the 1.123, and I get 5.50, 509, you know what, I'll say 5.51 whenever I round. That's going to be measured in milligrams again. So some things to notice, and this is our answer. But let me talk about it for just a second. It tells us the half-life up there is 64, and is that 64 and an eighth hour. So it makes sense, because this sat on the counter for more than that, it sat there for 72 hours, that just over half of it disappeared, or it disintegrated, or whatever we call this, right? Starting off, we had 12. If it sat on the counter for exactly 64.128, then there would be 6 left, right? But it sat there for 72, which is more than that, so it's a little bit less than 6. So that's how we do that. That would be like numbers 7 through 9 on your homework. So that's that. I think you guys are set up. Let me know if you have any issues.